The Riemann hypothesis is a conjecture on the pattern of zeros of a specific function arising from its inherent symmetry. Much like a parabola, which can have at most two real zeros, is symmetric, meaning we can find out their pattern provided we know its symmetry. We can also factor it over a product of its zeros, x minus a times x minus b. What about a more reclusive function, the Riemann zeta function? What is so special about this function? Let's write out our zeta function. Now let's multiply everything by 1 over 2 to the power of s. Now let's subtract this new expression from the original zeta function. Notice that this new expression has had all of the even multiples removed. Now let's multiply everything by 1 over 3 to the power of s. Now let's subtract this new expression from the original zeta function. This new expression has had all of the reciprocal multiples of 2 and or 3 removed. And we can do this infinitely many times, but we mustn't do it for every single natural number. We've already removed all of the multiples of 4. We must remove all multiples of prime powers, since every integer is a unique product of primes. So, equals 1. And then we can write the Riemann zeta function as an infinite product of prime powers. Since this function encodes information about prime powers, Riemann hypothesized that if we could factor it over its zeros, we could find a pattern in the primes. Our function doesn't equal 0 on the real numbers, but what if on the complex plane, where numbers have 2 dimensions, real and imaginary, and functions take one 2-dimensional number and map it to another? This is zeta function in the complex plane. Ah, but it still does not equal 0. Out of desperation, let's try multiplying the original sum by 2 over 2 to the power of s. Now let's subtract this from the original sum. Let's call this function something, phi of s. Let us now graph this function. Here comes the real part, here comes the imaginary, and oh my, I cannot believe my eyes, a 0! The function phi of s is defined for when the real component of s is greater than 0. Hence, we can rewrite our Riemann zeta function in terms of phi of s for the domain of the real component of s greater than 0. Now let that soak in. What we have just given is a definition for the zeta function that, while simultaneously agreeing with its original definition, is actually more generally defined for a greater domain. We have just performed analytic continuation. Let's continue zeta function to the entire complex plane. The method is really analogous. We use functions that are more defined than the zeta function, then define the zeta function in terms of these functions. But instead of using phi, we use the gamma function and the Jacobi theta function. Endure the beautiful analysis and feast your eyes on this. Rather, notice that when zeta of s equals 0, the entire expression equals 0, and the same is true for zeta of 1 minus s. It's symmetric, just like our parabola. Therefore, the zeros must be symmetric. A symmetric mapping of s into 1 minus s, 2s into 1, s into 1/2. That is it. The Riemann hypothesis, all non-trivial zeros, the zeros that we care about, of the Riemann zeta function, lie on the line with the real component of 1/2. So what's all of us? Well, the factors depend on the zeros, and if the zeros have pattern, then so do the primes. Well, what's the pattern? Asymptotic, just like we thought, but also periodic. That is what is meant by the primes have music in them.